All right, thank you for the invitation. So this talk is based on a few papers, one which I came out with by myself a couple years ago, and then two papers I've had in the last year with Connor Bean and Pietro Ferro, who are both postdocs. Um, okay, so probably many people here probably don't know what F-theory is, so I can start with kind of a brief introduction. Although to be honest, you don't need to know that much about it for this talk. Frankly, I didn't know what it was until I started working on this. Um, so F-theory is a geometric toolkit for studying type 2b compactifications in the presence of D7 branes. Now, why is it you need a whole special toolkit just for D7 branes? The reason is that D7 branes in string theory are magnetic sources for the RR axion. This is basically because the fact that the field strength for a D7 brane is an 8 form, and then the dual is a 2 form, and so then the magnetic version is coupling to an axion. And so what is the axion in string theory? Well, it's basically combined with the string coupling to get what we call the complexified string coupling. You know, that's the thing which transforms into S to Z duality. And so because these D7 branes are coupling to this axion, their back reaction makes the complexified string coupling some finite value. So generically, it's going to be strongly coupled. And this is why it's particularly challenging to study string theory in the presence of D7 branes, much more challenging than studying it in the presence of pretty much any other brane. And so in particular, what F-theory is that it's basically a way of using this SL2Z duality, or I guess modularity in the context of this conference, to constrain the possible values of the string coupling non-perturbatively. And so I'll explain in a bit more detail what this toolkit is in the coming slides, but that's kind of the basic idea of what F-theory is. So it's not like M theory, it's not like an actual physical theory, it's just methods to study type 2b string theory in the presence of D7 branes. Now, why is it that people care so much about type 2b string theory in the presence of D7 branes? Now, there's a couple of reasons. Broadly speaking, you could say that most realistic compactifications of string theory actually come from F theory, i.e. D7 branes. So for instance, this was some kind of fun recent paper where they showed how you could construct a quadrillion standard models by compactifying in the presence of D7 branes. And just kind of generically, I guess like the widest variety of string compactifications require you to have D7 branes. Secondly, from a more formal perspective, if you just want to understand possible UV completions of supergravity, which is I guess what the swampland program is trying to do, it turns out that in high dimensions, such as 6 and higher, pretty much all consistent low energy theories of gravity come from F theory. So F theory is a much more powerful way of constructing compactifications than, say, the heterotic string or M theory or other such methods. So it might seem very specific, D7 branes, but actually turns out to be quite general. So now, what's the problem with the F theory approach to studying D7 branes? So the traditional F theory toolkit can only show the existence of a low energy theory for some finite value of complexified string coupling. But it cannot tell you how to systematically compute corrections to this low energy theory, aside for some special protected terms, in which case you use some dualities. And so the reason why it doesn't tell you how to do that is that the string coupling is finite. And when the string coupling is finite, then you don't have a world sheet. And usually the only way we know how to study string theory is with a world sheet, which is like a small string coupling expansion. So the challenge is very similar to the case of M theory. So M theory we understand is strongly coupled type 2a string theory. And so because the coupling is strong, similarly in M theory, there's no systematic way of computing corrections to its low energy description. So in general, with any kind of string theory or M theory, we always know the low energy description. So in the M theory case, it's 11-dimensional supergravity. In the F theory case, it'll be some kind of like 8-dimensional super Yang-Mills. So that we understand. But there's just no systematic way of computing corrections. And this is an actual practical problem for people who are trying to construct the standard model starting from F theory compactifications. Because they basically don't have control over their compactifications beyond the leading low energy limit. And so this is why if eventually we would like to actually make predictions of the real world using string theory, we need to understand how to systematically compute these corrections. And so that's something I'm going to do in this talk for the first time. Okay, so the general approach which I'm going to take is this thing I've been working on for a few years, which is basically using the ADS CFT principle combined with some non-perturbative methods of solving the CFT. And so this is kind of encapsulated in this picture you see here. So first, let's consider quantum gravity in asymptotically anti-de Sitter spacetime, which you could think of as the cylinder over here. And so according to the ADS-CFT correspondence, quantum gravity in this space-time is supposed to be dual to a conformal field theory, in some sense living on the boundary of the space-time, which doesn't have gravity, but it has n degrees of freedom. And so then the correspondence says that when the Planck length is small, that's the same thing as the number of degrees of freedom in the CFT being large. So that means large n is dual to the gravity regime, so the low energy description of your string theory. Furthermore, the correspondence says that scattering of gravitons or gluons in quantum gravity and ADS is dual to correlation functions in the CFT. And so the idea is to compute a CFT correlation function in the CFT using some non-perturbative methods, such as conformal bootstrap or supersymmetric localization, which we will discuss. And you could do this both for large n and even for finite n. And so that's this picture over here, because that's dual to the scattering of gluons or gravitons in ADS. And then there's a precisely understood flat space limit, which allows you to take the cylinder to infinity, such that you then just get scattering of gluons or gravitons in flat space, which is what's called the S matrix. And if you know the S matrix, that's completely physically equivalent to knowing corrections to the low energy expansion, because the two are the same thing. It's like a low energy expansion is just an object which allows you to generate an S matrix and vice versa. And so if you were able to compute the CFT correlators to arbitrary order 1/n, then you were able to compute corrections to the low energy description. And I want to emphasize that you could do this in flat space. So you're not limited to ADS. You can get kind of the most general flat space expansion. So that's kind of the general strategy. So this is a strategy I've been pursuing with various collaborators over the years. And so in the past, we had applied it to the case of graviton scattering, which is related to closed string scattering. So for instance, in the case of type 2B string theory in ADS 5 cross S5, which is dual to a CFT called n equals 4 super Young Mills in 4 dimensions, by studying the CFT in a large n expansion, we were able to compute the first two higher derivative corrections to the low energy description of string theory. So if the leading low energy description of string theory is gravity, which is the whole point because it's a theory of quantum gravity, so it has higher derivative corrections because gravity is non-normalizable. And so the first couple higher derivative corrections, we write them as r to the 4 and d to the 4 r to the 4, where r is like the Riemann tensor. And so these corrections have coefficients which are functions of the complexified string coupling tau. In fact, they're modular invariant functions, in the theme of this conference. And so in these papers with some of the people in the audience, we were able to compute the coefficients at finite string coupling to these first high derivative corrections, and indeed they matched some predictions in the flat space limit. Furthermore, we were able to go beyond large n, and we were able to also study the CFT correlator at finite n and finite coupling, which I did in this numerical bootstrap paper a couple years ago. And this allows us to understand the ADS amplitude at finite alpha prime and finite string coupling. And so this is going beyond just protected terms. Another application of this program was to study M theory on ADS 4 cross 7 mod CK. So this theory of quantum gravity is dual to a CFT in 3 dimensions called ABGM. And in this case, we were also able to compute the first high derivative correction, r to the 4, which in this case kind of interpolates between M theory and type 2A string theory. And then similarly, we also were able to study the CFT at finite n and Chern-Simons level k. So this is just a review of an application of this general strategy of studying CFT correlators using bootstrap and localization in order to study the holographic correlator and then taking the flat space limit to learn about the low energy effective action. But in this talk, we're going to not talk about closed string scattering or gravitons. We're going to talk about open string scattering, which will be gluon scattering on branes, in particular D7 branes, because we want to talk about F theory. So in particular, the goal of this talk is to study the low energy theory on D7 branes in F theory at finite string coupling by applying the methods of bootstrap and localization to the CFT that will be dual to this F theory setup, which will turn out to be a 4-dimensional CFT. So the outline is as follows. First, we're going to describe the D7 brane low energy theories in flat space. Then we're going to talk about how to add some probe branes to make them go to ADS, and then we're going to discuss their CFT duals. This will all be a review. Then we're also going to review kind of kinematic constraints on a 4-point function in the CFT, which is dual to gluon scattering on the D7 branes. Then we're going to get to new material, which is how to use supersymmetric localization to constrain this quantity for finite n and finite string coupling. we're going to apply these constraints first at large n and finite coupling to compute some protected corrections, the low energy theory. And in some cases, there'll be some kind of weak string coupling limit. In other cases, the string coupling will be fixed. And then finally, we're going to discuss how to study this holographic correlator at both finite n and finite string coupling using numerical bootstrap. Okay, so let's start with the description of the F-theory setup. So here is where I'm going to explain what I meant by the F-theory toolkit. So basically what F-theory does is that it tells you that you're able to study properties of this string compactification on D7 branes by looking at a certain elliptic curve on a K3 singularity. So this is a curve defined as y as a function of x. And then these coefficients, G2 and G3, they are a function of z, and z is the complex coordinate which is transverse to the world volume of D7 branes. So in general, for any p brane, the low energy description on a p brane is a p plus 1 dimensional super Yang-Mills theory. So if it's D7 branes, then the low energy description on the 7 branes is some 8-dimensional theory. But string theory lives in 10 dimensions. So that means there are 2 transverse dimensions between the theory on the D7 brane and string theory. And so we can combine those 2 real dimensions into one complex coordinate z. And then this elliptic curve is going to tell us how the string coupling tau depends on this complex coordinate z. And that's basically what F-theory does for you. It tells you this dependence. Now, in our specific case, we want to look at the simplest examples of F-theory, and that's where tau is actually independent of z. And so those are a very restricted case of F-theory solutions. I mean, the vast majority of cases depend on z. If you want it to not depend on z, then the only way that's possible, using some kind of geometric facts about this elliptic curve, this can only be the case if this J modular function, whose definition I won't give, but I guess this is a modular conference, so people should know what that is. So tau is not a function of z when this J function of tau equals G2 cubed divided by the discriminant of this curve, where the discriminant is defined here. And so there's very few cases where you can actually solve this equation. And so the unique list of solutions to this equation are given in this table here. I mean, I'm actually missing one. The one I'm missing, though, we're not going to talk about because that doesn't have any symmetry associated with it. But forgetting about that one for now, so these are all the possible solutions to this equation. So these are all the values tau can take. So you see that either tau is fixed to a specific value, like I, or e to the I pi over 3, and then there's one special case where you actually have a solution for any value of tau. And then on the top line, these are basically the singularities on the K3 described by the elliptic curve when you have solved this solution in that specific way. And so this is like the unique list of such solutions. This was first shown by Ashok Sen in, I think, 1997. So now that we know the possible values of tau, so now we want to discuss the low energy theory on the D7 brane. So on general grounds, for any p brane, as I've mentioned, the low energy theory is always just going to be super Yang-Mills plus corrections. So in our case, it's going to be super Yang-Mills where the gauge group is exactly the singularity G given here. So this is SU2, this is SU3, this is SO8, and then these are the various exceptional groups. And so you're going to get a super Yang-Mills with those gauge groups in 8 dimensions, but there's also going to be infinite higher derivative corrections. And so the leading term that's what's kind of given to you by the simplest version of F-theory. But F-theory does not tell you how to compute the coefficient of higher derivative corrections, such as this f to the 4, or further higher derivative corrections. And so that's kind of the goal of this talk, is to figure out how to compute these higher derivative corrections to the low energy description of D7 branes. Now, as it happens, this first higher derivative correction, f to the 4, is protected. And so it turns out you actually can compute it using the fact that there's a special duality which relates type 2b string theory to the heterotic string. And then when you look on the heterotic string side, the theory is weakly coupled, and that's how you're able to actually compute the coefficient of this f to the 4. And so this was shown by these authors back in the late 90s. But this is a very special trick, and so this trick doesn't work for any unprotected terms. Another thing you know how to compute just from the leading low energy term is you could compute gluon scattering, because this is a theory of gluons, it's super Yang-Mills. And so you could compute tree-level gluon scattering, which is finite. You could also compute a one-loop gluon exchange term. And so that has a logarithmic divergence in 8 dimensions. Another diagram you could write down. So notice that there's also gravity here, right? Because we're coupling to the 10-dimensional metric. And so you can also compute the tree-level graviton exchange term. which comes from the fact that your gluons are coupling to gravity, via this overall factor. And so because we are discussing 8-dimensional Yang-Mills, but in a 10-dimensional spacetime, thus the tree-level graviton exchange term is actually also logarithmically divergent. This is basically due to the integral over the two transverse dimensions. So both of these diagrams are actually logarithmically divergent, but because string theory is a finite theory, they have to be regulated by string theory, and so they're going to generate terms that look like the log of string length. And so, but we know exactly what those coefficients should be because that just directly follows from the leading low energy term. So the real question is how to compute higher derivative corrections d to the n f to the 4 when n is bigger than 2. Because those are the higher derivative corrections which are not protected, for which there is no method currently of how to be able to compute them. And so that's kind of like the general idea of the talk, is to discuss how to be able to do that. Okay, so far we just discussed D7 branes in flat space. Now, in order to apply the methods of ADS-CFT, we want to be able to go to anti-de Sitter space. And so the way we do that is that we probe this F-theory setup with n D3 branes. And we basically make them coincident with these D7 brane singularities. So when you have many of these D3 branes, this is kind of following the general logic of ADS-CFT, they warp the geometry such that you can kind of forget about the D3 branes, and now instead of flat space, you now have some ADS factor times some compact spacetime. So if this was n equals 4 super Yang-Mills, where you didn't have D7 branes, but you just had n D3 branes, then your spacetime would have been ADS5 cross S5. Because you have D7 branes, instead of S5, you have this X5, which is like a deformed sphere. So in particular, it's a 5 sphere, but the azimuthal direction phi has a deficit angle written in terms of this nu. So basically it means that like when you kind of go around the circle, it's like a cone, and it changes by this nu. So for all the different singularities we discussed, this is the value of nu. So just to kind of connect this to what you might be more familiar with, if this was n equals 4 super Yang-Mills, then nu would be 0, because then phi would just go to phi plus 2 pi. But now that you have D7 branes, nu is non-zero, and these are the various values for these singularities. So this is a spacetime with a singularity, and so you can look at the fixed point locus of that singularity, which is ADS5 cross S3. And so notice that 5 plus 3 adds up to 8, and that's expected because if you now take the flat space limit of this spacetime, you just get the 8-dimensional world volume of the D7 branes, which is the thing we discussed on the previous slide. And so connecting to kind of the original strategy we discussed in the beginning, the idea is that we're going to study some CFT, which is going to be dual to this ADS5 cross S3. And then at the end of the day, we're going to take a flat space limit, which is then going to teach us about the D7 brane world volume. As usual in ADS-CFT, there's going to be a dictionary between the bulk parameters and the CFT parameters. So the bulk parameters is the string length as well as the ADS radius L. And then in the CFT, we're going to have n. You could also interpret n as the number of D3 branes. And then this delta bar is just some function of nu. Later on, we'll give it another interpretation. But for now, you could just think of it as something which is related to nu. So again, if nu was 0, as an n equals 4 super Yang-Mills, this would just be the usual ADS-CFT dictionary. Okay, so what is the CFT that is dual to this ADS setup? So because we have an ADS5 factor, thus we expect it's a 4-dimensional CFT. It has half maximal supersymmetry, and it has a flavor symmetry, which is G. Remember, G was the various groups SU2, SU3, SO8, E6, E78. And then there's also another SU2 factor. And then because you have half maximal supersymmetry, you always have an SU2R cross U1R as well. So the simplest example of the 7 theories we've discussed, or I guess really 6 theories, is the D4, i.e. the SO8 theory. Because in that case, you can actually write down a Lagrangian for this dual CFT. So in that case, the Lagrangian is a USB to N gauge theory with 4 hypermultiplets in the fundamental and 1 in the antisymmetric, where the complex gauge coupling of this gauge theory is related to the complex string coupling. Now, the reason why you have a Lagrangian is because this is the special case where tau could take any value. So you might remember from the previous slide, I was saying the allowed values of tau, and I said that specifically for the D4 theory, tau can be any value. And that's why it has a Lagrangian. For the other CFTs, though, I said that tau had to take a specific value. It had to be either I or e to the I pi over 3. And that means the dual CFT does not have a Lagrangian description. Instead, the CFT it's dual to are these non-Lagrangian theories. Specifically in the case of the SU2 and SU3 theory, these are rank N Argyris-Douglas theories. And then in the E6078 case, these are rank n Minahan-Nemeshamsky theories, which are just named after the authors who first discovered these non-Lagrangian theories, I guess, roughly 20 years ago. Okay, so what is the quantity we are going to study in the CFT? So we are going to consider the 4-point function of the flavor multiplet in the CFT, which is then dual in the bulk to gluons scattering on the D7 branes. So from the CFT perspective, we can consider the superprimary of the multiplet which includes this flavor current. So the superprimary is just a scalar of dimension 2, and it has an adjoint index under the global symmetry group G, and then it also has another index under this SU2R symmetry. So if we consider a 4-point function, we can expand it in the representations that appear in the tensor product of two adjoints. And so depending on the group, different kind of representations will appear, and I will kind of discuss them case by case. So the general idea is that you expand it in these representations, and then you can write the 4-point function as a function of these combinations of positions, which are called conformal cross ratios, and then it's also a function of this combination of these SU2R polarizations. One then should impose the constraints of supersymmetry, and those are completely captured by something called the superconformal word identity, which has an exact solution shown by Dolan and Osborne. And so basically the solution is that you take this function g, and instead you write it as a function fancy g, just factoring out this z and w, where z is related to u. And so at the end of the day, if we consider this fancy g, then we have automatically satisfied the constraints of supersymmetry. There's also this other short piece, but this piece is a bit trivial. So then the goal of the remainder of this talk is to study the 4-point function as encoded in this function g, where this subscript r means that we have a different g for every representation in the tensor product of two adjoints. And so that's our goal, is to study this g. Okay, so how can we constrain this g? So we want to try to focus on non-perturbative constraints if possible. So first of all, we have crossing symmetry. And then if we study the theory at large n, we also have some expectation of analyticity of the Witten diagrams that should contribute. And so this is what's called the analytic bootstrap. And it turns out that it fixes the functional form of G in a highly constrained way. So at leading order in the large n expansion, there's just a unique function you could write down, which is what I call GF squared. And then at subleading order, there's a small set of functions you can write down, which is what I write here. So these coefficients k and c, k scales linearly with n, and c is quadratic in n. The exact form is known, but it's not so important. So the point is that this is 1 over n, and all these other terms are 1 over n squared. And so these three terms are just completely fixed by the constraints of crossing symmetry and analyticity. So they're a bit trivial, you might say. The terms that are non-trivial are these two sets of terms. For these terms, we only know how to fix them up to these coefficients b, where the number of coefficients b is related to the number of quartic Casimirs of the flavor symmetry. What's the physical interpretation of these terms from the bulk perspective? So from the bulk perspective, the leading 1 over n term is a tree-level exchange of gluons. This is why I write f squared, because f squared is the kinetic term for Yang-Mills. So that's to remind you that this is tree-level gluons. And so similarly, g f squared is a one-loop diagram in the bulk, in ADS, with two vertices corresponding to gluons. And so this is completely fixed. This gr is the tree graviton exchange, where I wrote r to remind you of the Einstein-Hilbert term. This too is in principle fixed, although in practice it's a very hard calculation, and so people haven't fixed it yet. But it should be possible to be able to fix this term. And so all these terms are fixed because all these terms basically are given to you by the leading low energy description, which is kind of the thing I was saying we already know. So the thing which we don't know is the higher derivative corrections. So the first higher derivative correction shows up here. So we would contribute to this term in the amplitude, which is f to the 4. And so its coefficients are not fixed just by symmetry and analyticity. For that, we need additional input. Another term which is not automatically fixed is this log n term. This log n term corresponds to the fact we discussed before that in 8 dimensions, you have a logarithmic divergence for the one-loop gluon exchange as well as the tree-level graviton exchange. And so if this wasn't a theory of string theory, if this was just Yang-Mills in 8 dimensions, you would just have a divergence and you would say the theory is sick and you'd have to throw it out. But because this is a low energy description of string theory, which is UV complete, thus we know that all divergences must be regulated. And so we know that there must be a way of basically taking, like, assigning a finite number to this divergence. And so there should be a log n with a specific coefficient multiplying it. But that coefficient is non-trivial because this is something which is being taught to you by string theory. And so this is something which, again, you will need some physical input in order to compute. And so in practice, for the remainder of the talk, I'm going to be describing methods to compute the coefficient of this log n, as well as the coefficient of this f to the 4 term. Okay, so what are the methods I'm going to use to compute these coefficients? So I'm going to use supersymmetric localization. So for any 40 n equals 2 CFT, you can always deform your action by a mass m that couples to the flavor multiplet of the group G. And then if you take derivatives of this mass m and then set m equal to 0, because the mass couples to the flavor multiplet, that will give you integrated correlators on the sphere of the flavor multiplet. This is just the usual idea in quantum field theory, that if you have a source coupling to an operator, and if you take derivatives of the source, then it gives you integrals of that corresponding operator. So in this paper a couple of years ago, I worked out the group theory, and I showed that the precise relation for taking 4 generic derivatives of masses, setting mass to 0, is related to this specific integral of the 4-point function, written in terms of this fancy g, for the various representations that could occur. So in general, you have many different masses, because the number of masses is basically going to correspond to like the rank of the adjoint of your group, the number of Cartans. But not all these mass derivatives will give you independent constraints. So it turns out the number of independent constraints is related to the number of quartic Casimirs, which is related to the fact that we're taking 4 derivatives. And so recall from the previous slide that the number of quartic Casimirs was also exactly how many of these coefficients b we have. So we see that we have exactly enough constraints from this integrated constraint to be able to fix all these coefficients b, which is exactly what we're going to do. Okay, so now let's implement this program for the specific theories, and let's start with the simplest theory, which is the D4 theory. It's the simplest one because it has a Lagrangian. So remember, this is a USB to N gauge symmetry with this matter content, where I should note that when n is 1, this is the same thing as SU2 conformal SQCD. So in this case, the adjoint is the 28 of SO8, and when we take the tensor product with itself, we get the following representations. The most interesting ones to focus on are these 335 representations. Because recall that the group SO8 has a triality symmetry. And so that means representations comes in pairs of 3. And so something which is interesting about this specific theory is that the way the duality group SL2Z works is that it has a non-trivial relation to the triality frame. And so this means that when you do S duality, it changes V representations to C representations. Similarly, when you do T duality, it changes C representations to S representations. This was first shown for SU2 SQCD by Zyberg and Witten in their classic paper from the mid-90s, but it's also true for this entire class of theories for any value of n. Another kind of detail is that the coupling you would define in the UV that shows up in the Lagrangian is not the thing which transforms naturally under this duality group. Instead, it's related by this non-trivial function that's shown by these authors. The fact that you have a duality group is simply just because you have a conformal manifold. So basically, you have like a family of theories parametrized by the value of tau, and for every single value of tau, it's a CFT, and they are related by this duality group SL2Z. Okay, so how many integrated constraints do we have? Well, we have 3 quartic Casimirs for SO8. And so this means that there should be 3 independent combinations of 4 derivatives of the 4 masses. And so we can arrange them as follows into these 3 linear combinations. And then these 3 linear combinations then are related to integrals of these combinations of the g function. So these are just the different representations which show up in the 4-point function. And as you see, these 3 combinations, they basically just differ by a sign. So there's a sign either on 35S, 35C, or 35V. And so they're related by triality, as you would expect. Okay, so in order to actually learn something from this relation, though, we need to be able to compute what the mass derivatives of this free energy is. Otherwise, we would just be relating an integral to something we don't know. But the point is that we do know how to compute the derivatives of the free energy. So it was taught to us by Pestun 10 years ago that if you have enough supersymmetry and if you have a Lagrangian, then you can simplify the path integral of the free energy in terms of a matrix model integral, which takes the following form. So for gauge group G, X is basically the Cartan elements of G. So in our case, G is USB to N, and so it's an n-dimensional integral. And then the dependence on tau is most non-trivially given by the Z instanton term. Other than that, you just have a dependence on Yang-Mills, which is just the imaginary part of tau. So we're going to study this theory in kind of two limits. First, we're going to consider the limit where we ignore instantons, which is called the Tuft limit, and that's a bit easier. And then afterwards, we're going to consider the limit where we include instantons. And that limit has this SL2Z modular invariance. So I should note that this theory is kind of more complicated than n equals 4 super Yang-Mills, because at n equals 4, when the mass is 0, you would actually have a free matrix model, whereas in our theory, it's interacting even when the mass is 0. Okay, so let's first talk about the limit large n and large lambda where we can ignore instantons. So there was a nice paper by Zeitlin and co-authors from a couple of years ago where he showed they could use the Toda equations to compute the mass to form free energy to every order in 1 over n and 1 over lambda. So he kind of totally solved the problem perturbatively, and he got the following answer. So this combination of 4 mass derivatives has a log lambda and then some function of n. The function is known, but I won't tell you what it is because I don't care about it so much. And then for the other combinations of 4 mass derivatives, you just get a 1 over lambda term, a log lambda, and then again, just some function of n. So you see that the dependence on lambda is extremely simple. It basically truncates at like subleading order. Just to be clear, what I define as lambda is in terms of the IR coupling. So it's kind of differs by a shift from like the UV lambda. So it's very kind of surprising that these mass derivatives have such a simple dependence on lambda. Because if you were to compute the analogous quantity in n equals 4 super Yang-Mills, which I did a couple years ago, or I guess a few years ago at this point, then you would have found that at every order in 1 over n, there is 1 over lambda dependence to every order in 1 over lambda. So n equals 4 super Yang-Mills is actually more complicated than this theory. So this is a sense in which this theory is actually the simplest theory, because it's even simpler than n equals 4 super Yang-Mills. You see it as very simple lambda dependence. Okay, so now that we know the answer for these derivatives of the mass to form free energy to any order in 1 over n and 1 over lambda, we can then use it to constrain the 4-point function using those integrated constraints I discussed in the previous slide. So in particular, we can use it to fix those coefficients b. So the coefficient b up to the f to the 4 high derivative correction you can fix, and it's proportional to zeta of 2, because notice there was a zeta of 2 here. And similarly, you can also fix the coefficients b corresponding to the logarithmic threshold term, the log n. So you can fix both of those guys in this limit. And then as a consistency check, you can take the flat space limit, and this should match to what you expect from the 8-dimensional world volume, which is actually equivalent to the Veneziano amplitude. Because the Veneziano amplitude is just scattering of gluons at leading order, and that's exactly what we have. And so indeed, the f to the 4 term matches the Veneziano amplitude. Similarly, the log n term matches the expected logarithmic divergence in 8 dimensions. Furthermore, it turns out that the next correction was d squared f to the 4 that's also protected. And so that was known in flat space, and you could use that to fix the ADS d squared f to the 4. So it turns out you can actually go beyond just the leading higher derivative corrections. So you can go beyond this protected d squared f to the 4 term. And so I had a paper with these authors very recently, just a couple months ago, where we use a method developed by Fernando and Tobias in their previous paper, which is that it basically requires 2 ingredients. First of all, you propose a certain dispersion relation that relates the 1 over lambda expansion to certain operators that scale positively with lambda, which correspond to massive stringy states. They go like lambda to the quarter. And second of all, you assume that your answer for the CFT correlator at order 1 over n, but all orders in 1 over lambda, you assume that it should be given by some kind of world sheet integral. Because I guess on general grounds in flat space, you compute scattering of strings by doing some kind of integral. For open strings, this would be a 1-dimensional integral. And so you just kind of conjectured that now that we're doing this in ADS, it should be similarly given by another 1-dimensional integral with some restricted set of integrands, which we call multiple polylogarithms. So with this ansatz, it turns out we were able to compute all higher derivative corrections, including the non-protected ones, but in a large ADS radius expansion. And so there's kind of like 2 methods here. The first method, which uses localization, this allows you to compute just the first couple protected terms, but at finite ADS radius L. The second method allows you to compute all the high derivative terms, including the unprotected ones, but only in a 1 over L expansion. And so as a consistency check, you can check the first couple protected terms, and indeed they match. And so that's kind of a check on this method. But this slide is more of an aside. This isn't the main focus of the talk. I was just to point out that we actually have been able to compute higher derivative terms. Okay, so now let's move on from the large n, large lambda limit, which corresponded to weak string coupling, and let's talk about large n finite tau, which is maybe more apropos to this conference because this is where modularity will come into play. And so at large n and finite tau, first of all, we can consider the perturbative in tau terms. So the perturbative in tau terms are just trivially related to the lambda terms, because lambda is just the imaginary part of tau. And so from the previous slides, we can just immediately read off that the perturbative terms are given as follows. And so the whole challenge now is to compute the instanton contributions, because that's what we need to get finite tau. And so for that, we need to consider this z instanton contribution to the matrix model, which can be written in terms of instanton sectors k. Now, unfortunately, this z instanton is not actually known in full form, despite what the literature says. So in general, it's very complicated to compute the z instanton. So this was famously first done by Nekrasov in the case of UN gauge groups. And that's the case where everything is well defined. But if you want to apply Nekrasov's formalisms to other gauge groups, such as USB2N, it turns out that it's much more subtle. So the way Nekrasov went about computing this in his paper with his student Shadchan in the early 2000s is that they, instead of studying the sphere free energy in 4 dimensions, what we're interested in, instead they studied an index in 5 dimensions, which is S4 cross S1. And the reason why they did that is they wanted to avoid some divergences that showed up if you tried computing the z instanton directly in 4 dimensions. And so they consider the answer in 5 dimensions, and then they take the limit where this S1 becomes really small to try to then recover the z instanton just in 4 dimensions. And so after taking this limit and being kind of cavalier with singularities, they made a proposal that this is what the answer for zk should be. So they said that for like generic matter content, so if you have vector multiplets, hypermultiplets, as well as antisymmetric multiplets, the answer should take this form where these functions are some known functions. So they had this proposal. And so this proposal works in the simplest case where you don't have antisymmetric multiplets and you only have vector multiplets and adjoint multiplets, which would be the case for n equals 4 super-Yang mills. But this proposal does not work when you have a more complicated set of matter fields. And so they were a bit sloppy in their original paper. It's kind of funny to say that Nekrasov is sloppy, but in fact he was. And so the naive expression for the z instanton which Nekrasov wrote down has several problems. So first of all, at large n and finite tau, using his naive formula, we would find that all the instanton terms, which would come from the z instanton, are exponentially small in n. And so this just violates SL2z, because then the answer we would get would not be SL2z covariant as it has to be. So that's why we know the answer is wrong from his naive formula. We can also check that it violates SL2z even at finite n. In that case, you can just do the matrix model integral numerically, and you see that it just does not satisfy SL2z. Another check that this is wrong is that the contribution for the antisymmetric multiplet is non-trivial even in the USB2 case, but in that case it should be trivial, because USB2, there just is no antisymmetric multiplet. It's not defined, because it's the same thing as a singlet. And so that kind of also shows that his naive formula has some kind of mistake. Similarly, the USB2 theory is supposed to be the same thing as the SU2 theory, because these are the exact same group. But for SU2 SQCD, we know the answer for this matrix model quantity, because this was computed using the AGT formalism, many years ago. And it just doesn't match what you get from Nekrasov's naive formulation. In fact, it only matches if you drop the antisymmetric contribution by hand. But there's no kind of justification for that. So it turns out that all these problems, which we discovered in Nekrasov's formula in 4D, there's actually analogous problems even in 5D. So even for the S4 cross S1 formalism, there was also a problem in the formula Nekrasov wrote down. So the problem in particular is that in this 5-dimensional case, you have these 5D CFTs, and they're expected to have a certain enhanced global symmetry, in particular E5. And it turns out that if you use Nekrasov's formulas, you don't get that enhanced symmetry. So you also know that they're missing something even in 5 dimensions. And so this problem was first pointed out by these authors in the case of 5 dimensions. And so in the 5-dimensional case, the way they solved this problem is that they said that you have to add an extra term. So instead of just Nekrasov's instanton term, you have to put in this thing which they called Z extra. And they had some kind of justification of why you have the Z extra, which I'm not going to go into. But the point is that the Z extra is independent of the matrix model eigenvalues, and that means that it's the same for all values of n. So in 4 dimensions, we didn't try to actually derive Z extra because we didn't know how. In principle, we thought maybe you could get it from dimensional reduction from the 5D one, but that was too difficult. So instead, the way we derived z extra in 4 dimensions is that we just assume that z extra should be n independent, as it was in the 5D case. And then we also demand that the USB2 theory should have to be the same thing as the SU2 theory, because that must be true, because they're supposed to be the same theory. And so then if this thing does not depend on n, and when n is 2, it has to be the same thing as a known function, then that is sufficient to teach you what the z extra should be. And so at the end of the day, we found the following form for z extra, which is written in terms of this gnome q, which is e to the I pi tau. And so we found this for kind of generic values of mass. And so after using Nekrasov's formula, adding in the z extra, then we were able to compute the instantons, and yes? Yeah, they're the 4 masses, 1 mass for each SO8 cartan. So, okay, so after this whole technical story, so mathematicians in the audience, this is what you can focus on. You don't need to see where this came from. The point is, at the end of the day, that we get these modular covariant functions. And so they are modular covariant because you see that, so these terms just depend on n, so they're trivial. All the non-trivial terms are here. So again, this is much simpler than n equals 4 super Yang-Mills. Because what I'm saying is that to every order in 1 over n, the only dependence on tau is at leading order, and all the tau dependence is captured by these modular covariant Jacobi theta functions. So what are these Jacobi theta functions? What's this theta 3 and theta 4? So the precise definition in terms of the gnome is given here, which I guess this audience hopefully is already very familiar with. So let's compare this to the answer which one would have gotten in n equals 4 super Yang-Mills. So at n equals 4 super Yang-Mills, if you would have computed the analogous quantity, you would have found that it would have been written in terms of these non-holomorphic Eisenstein series. And so non-holomorphic Eisenstein series, they have 2 perturbative in tau terms, and then they have infinite instanton terms. In contrast, the logarithm of these Jacobi theta functions, which is what we find, they have no genus corrections to the instanton terms. Because notice that these are just numbers. You know, like there's no function of tau which is multiplying these q's. There's just q's. And so the instanton terms are much simpler than n equals 4. Also, the Jacobi theta functions, after you take a logarithm, they're going to include a log tau too. And so this is related to the log lambda, and physically speaking, this is related to the fact that you have this one loop divergence which you had to regularize. Whereas in n equals 4 super Yang-Mills, you just didn't have such a logarithmic divergence, which is maybe why you didn't expect to get a log tau term. So we see that even at large n and finite tau, these modular covariant quantities are significantly simpler than n equals 4 super Yang-Mills. Okay, so now we can apply this answer to study the holographic correlator at large n and finite tau. So in particular, we can fix the coefficients b. So the coefficient b for f to the 4 is now written in terms of those modular functions. So it's written in terms of logs of Jacobi theta functions from the previous slide. And we can also fix the log n term, whose coefficient is just some number. So in the flat space limit, we can compare the tau-dependent parts of these coefficients to the coefficient of f to the 4 in flat space, which was computed, as I mentioned earlier, using the duality to the heterotic string back in the 90s. And indeed, we get a match. And so it turns out that back in the 90s, they also had these Jacobi theta functions. From their perspective, it came from some tree-level string calculation in the heterotic string, which is why you see Jacobi theta functions. Whereas from our perspective, it's kind of coming from a much more complicated calculation. Unfortunately, we cannot yet compare the tau-independent term. Because for the tau-independent term, we would have to compute this tree graviton exchange in ADS, and we don't know what that is yet. So that's why we only can compare the tau dependence. On the other hand, though, we could compare the log n term, and that also successfully matched with the right coefficient. Finally, in flat space, turns out you can compute not just f to the 4, as they did in the late 90s, but you could also compute this other protected term, d squared f to the 4. So we did this in our paper, inspired by a paper by Shai and Yifan Wang from a few years ago. Basically, we wrote down some covariant modular differential equation, and then we know the leading perturbative term, and so we found that the solution is a non-holomorphic Eisenstein. And so it turns out that whereas the leading term, f to the 4, involves Jacobi theta functions, the next term, d squared f to the 4, does involve a non-holomorphic Eisenstein, just like n equals 4. And then, using the fact that we know this in flat space, we can then use that to fix the answer of the ADS holographic correlator at this order. Okay, so this concludes the large n finite tau story for this SO8 theory. So now moving on to finite n, so now we're going to use numerical bootstrap. So the idea of numerical bootstrap is that we take our 4-point function and we expand it in conformal blocks, which is something you can do kinematically. And so then all the interesting non-trivial information is the coefficients of these conformal blocks, which are called these OP coefficients lambda, as well as the scaling dimensions delta of these conformal blocks. Then the next step is that we have crossing symmetry, which is the fact that you should be able to permute these 4 operators and the right-hand side shouldn't change. On the other hand, the block expansion does change when you permute it, and so demanding that the block expansion should be the same gives you a function's worth of crossing equations, which we write as this equation. Basically, this thing has to equal 0. And so in particular, there's 7 crossing equations. So in addition to these crossing equations, we can also add in the 3 localization constraints, which are the things we were discussing before. And that allows you to input the value of tau into your system of constraints. We're going to be studying finite n, so we're going to compute these mass derivatives. For the simplest case was USB2, in which case you can get it from HET. So after combining these crossing constraints as well as the localization constraints, we get the following bounds on the scaling dimension of the lowest dimension operators in the 35 representations for the 35V, S, and C. And so if you look at this plot, starting on the left-hand side, this is the free theory. So in the free theory, we know that one of these operators should be dimension 2, the other one should be dimension 4. And so our bounds are not fully converged, but they're pretty close to 4 and 2. And then as you start going to the right, you start going first to weak coupling and then to strong coupling. And then what you see, which is very nice, is that as you go to very strong coupling, as you go to tau equals I, you see that some of these representations, they merge. So what used to be dimension 4, what used to be dimension 2, they become the same dimension. Whereas what used to be the same in the free theory now becomes 2 different operators. And this is kind of expected, because this is related to the fact that duality has a non-trivial relation to the SO8 triality frame. So similarly, you can look at the region of tau going from I to e to the I pi over 3. And so then two of these operators are the same. One is different. And then as you go to e to the I pi over 3, they actually all merge into a single point. And then if you were to look at further values of tau, this whole cycle would just keep repeating periodically, because you would just go outside the fundamental domain and everything just becomes the same. And so these bounds, we conjecture, in the limit of infinite precision, are saturated by the physical theory. Thus, you could say that we have like a non-perturbative solution to this conformal field theory, at least for the specific quantity for the USB2 theory. Although, of course, we need better convergence. Okay, so that concludes the finite n, finite tau story for the SO8 theory, which had a Lagrangian. So in the last few minutes, we're going to discuss this other theory, the other sets of theories for which tau is fixed to a specific value, and in which case the CFT dual is one of these non-Lagrangian theories. So to remind you guys, these are the cases where it's non-Lagrangian. These are the values of tau, which it has to take. And then in the first 2 cases, it's Argyris-Douglas. In the last 3 cases, it's Minahan-Nemechemsky. So even though these theories have no Lagrangian, they can be considered as the infinite Coulomb branch limit of Lagrangian theories, which is in fact how these theories were discovered in the first place. So for instance, for this A2 theory, you could construct it by starting with SUN SQCD with 3 flavors, which is an asymptotically free theory. And then you can take the limit where you take your UV scale lambda and the center of mass of these 3 masses, of these 3 flavors, and you make them go to infinity with some fixed ratio. And then in that limit, which is an infinite Coulomb branch limit, you actually flow to a non-trivial CFT, which is this Argyris-Douglas theory. And this is why it has SU3 symmetry, because there's kind of like 3 flavors. There's a similar construction for A1, which has SU2 symmetry, starting with 2 flavors. And then similarly for Minahan-Nemechemsky, you can also construct it starting from some more complicated Lagrangian. So one thing which is common between all these theories, despite the fact that they have very different groups, is that they all have 1 quartic Casimir for all these global symmetry groups. So this is actually much simpler than the SO8 case, which had 3 quartic Casimirs. So the fact that there's just 1 quartic Casimir means that there's just 1 integrated constraint. And so that means for simplicity, we could just consider a single mass. So even though the number of masses in general is more than 1, because the number of masses is the number of Cartan. And so for E8, you would have like 128 masses or something. But there's no need to consider all 128 masses, because everything at the end of the day just depends on 1 mass, because there's just 1 quartic Casimir. And so again, the question is, can we compute this left-hand side? Can we compute this mass to form free energy, thereby using it to constrain the 4-point function via this integral equation? Now, what is challenging in this case is that these are non-Lagrangian theories. And so supersymmetric localization only works when you have a Lagrangian. And so you might think you are out of luck. And so the point of my recent paper was to tell you how you can compute this even though you don't have a Lagrangian. And so our proposal is that you could compute the sphere free energy in a small radius expansion, where this r is the radius of the sphere. This is the sphere. And in particular, you can compute it using the Seiberg-Witten curve, which is known for all these theories. So I should note that this wasn't an entirely original idea. So already 10 years ago, Rousseau had proposed that for finite n, there should be some way of computing sphere free energies from the Seiberg-Witten curve using a small radius expansion. And this idea had been used in various follow-up papers. The problem, though, is that at finite n, this proposal actually is not well defined, as you'll see in the next couple slides, because the quantity you get for the small radius expansion is actually divergent. And so this was kind of a problem with these previous papers, which is why they kind of only gave kind of very heuristic results. And so the novelty of our paper is that we're considering this proposal at large n, where things are a little bit better defined. And we actually have some checks on this proposal now. Okay, so let's describe what the Seiberg-Witten approach is. So Seiberg-Witten theory is basically the idea that when you have a 4D theory with n equals 2 supersymmetry, you can write down a certain elliptic curve that will tell you properties of the theory. So this is actually very reminiscent of F theory, because in F theory you have an elliptic curve, also in Seiberg-Witten theory you have an elliptic curve, and it's not a coincidence because it turns out they're actually related, by holography. But whatever, we're not going to talk about that relation. So the point is that you have some elliptic curve, which again is given by this equation y squared, and then it's cubic in x. You have these coefficients g2 and g3 as a function of u, and they're also going to be a function of the mass. And so we know what the Seiberg-Witten curve is for these theories, and so this is the coefficients for the various theories we consider. And I'm only considering the rank case right now. I'm not considering rank n, which is what I ultimately care about. And so the nice thing about the Seiberg-Witten curve is that you can use it to compute something called the prepotential. And so this prepotential, this f tilde 0, is written as an integral of these periods, omega 1, I think it's a typo, I think it should be maybe omega 2, where these periods are written in terms of G2 and G3 in this exact form, where these are non-holomorphic Eisenstein series. Oh, sorry, no, these are holomorphic Eisenstein series. Yeah, sorry, these are holomorphic Eisenstein series. And so this is, I guess, another example of modularity. It's a modularity conference where it turns out that like when you're computing periods of an elliptic curve, those periods are kind of naturally related to holomorphic Einstein series, which is kind of nice. So this is all kind of known stuff, and this is very general. So what is special about the theories we are considering is that you can actually compute the rank n Seiberg-Witten prepotential, and it turns out that it's just a sum of the rank 1 Seiberg-Witten prepotentials, where you just have a different value of u for each n. And this was shown by Michael Douglas and John Schwartz and David Lowe back in 1997. So this is a very, very special property, I should add. So like for a generic n equals 2 theory with a Seiberg-Witten curve, it's incredibly difficult to study it for rank beyond 1. So I think like the most people have done is like rank 2. So like the only case where you can actually study these Seiberg-Witten curves for arbitrary rank is these theories, because it turns out that the prepotential is so simple. Which is probably related to the fact you have this simple holographic explanation. And so to give a slightly physical description, like what are these u's? These u's are basically the expectation values of the Coulomb branch operators. And so you have a different one, when it's rank n, you have like 1 for every single rank. Okay. So why do we care about the Seiberg-Witten prepotential? Well, the Seiberg-Witten prepotential is, by definition, the r goes to 0 limit of the sphere free energy. And so that means that we're able to compute the leading term in the small radius expansion of the sphere free energy from the Seiberg-Witten curve. And so in particular, if we take our sphere free energy at finite radius, our usual f of m, so we can write this as an integral over these eigenvalues a of the small radius expansion. So here we have a small radius expansion. So the leading term has r squared. That's the Seiberg-Witten prepotential. And then you have infinite small radius corrections. So the first correction in small radius to the Seiberg-Witten prepotential, it was shown by a series of authors over the years that this is completely fixed by like modular invariance to take this form, which is a very general equation. And this is even known for the rank n case. So there's basically 2 terms. One term is the Jacobian, which goes from these u variables to the a variables, because the a variables is what kind of more naturally appears in this equation. The second term is the logarithm of the discriminant of the elliptic curve. Well, remember, I discussed the discriminant many slides ago, but the point is that the discriminant is just written in terms of G2 and G3. So the discriminant for the rank n theories we consider was considered by Shapiro and Tachikawa in 2008, and they showed that the rank n discriminant can actually be written in terms of the rank 1 discriminant, delta tau, in this very simple way. So basically, you have this term here, which involves like 2 u's, and then you just have a product over the rank 1 discriminants. So that means at the end of the day, we know how to evaluate this for our rank n theories. Now, ideally, we would also like to compute the higher radius corrections, so like the f of p's for p bigger than 2. Now, for rank 1 Zyberg-Witten curves, there's something called holomorphic anomaly equations, which tell you how to compute these corrections. But as far as I understand, it is not fully understood how to do this for rank n. Now, this literature is very mathematical, so hopefully some of the mathematicians in the audience might be motivated to look into this. Perhaps they already have. And it's possible that maybe people do know how to do it for rank n. But at least I wasn't smart enough to figure out how to do it for rank n. So if it is known, then it'd be great if somebody could tell me how to do that. But that's why in practice, I just used F0 and F2 for the results I'm going to show you. But I think it should be possible in principle to get the rest of the corrections. Okay, so anyway, so just using the leading prepotential as well as the first correction, and then using the way you write the sphere free energy in terms of this expansion, as shown here, you then get the following expression for the sphere free energy, in particular the sphere partition function. So this F2 gives you this term here, which basically looks like a Vandermonde determinant. And so that's kind of nice, because usually in matrix models we want a Vandermonde determinant, and that's what we get from F2. And then from F0, we get this term. So like this is kind of like a leading term, which has u to this kind of funny fractional power. And then the first mass correction gives you a log u with this coefficient f log. So the value of the c squared f is something we can compute because it comes from the Zyberg-Witten prepotential. But for what I'm going to talk about today, I'm not actually going to use its value. I'm just using the fact that this thing is real, i.e. c squared is positive. So that's the only thing I'm using about it. The value of f is much more important, and it turns out that for all the theories we consider, this f log is 1/2, which was not obvious. Like to get 1/2, we had to be like very careful with normalizations, but at the end of the day, it ends up being 1/2, and this is going to be very important. And so, of course, there's infinite more corrections, but I'm not going to talk about them. So the rest of the corrections would involve higher powers of mass, and they would also receive contributions from fp for p bigger than 2. But I'm just not going to talk about it. Now, there are several kind of conceptual challenges with this matrix model, which I'm writing down here. So first of all, there's infinite corrections to the potential, for which you need to know all the different fp's. And I should note that this expansion in small radius is kind of equivalent to a large U expansion. So it's kind of a large eigenvalue expansion. And so we don't yet know how to compute them. The next challenge is the fact that, as you see from this log U, clearly the matrix model has some, it's not well defined when U is 0. And so there's going to be some kind of question of how do you consider these branch cuts when U is 0? And if you were to get more terms, you get 1 over U to various powers. And so you have to figure out how to regularize it around U equals 0. This is one reason why I said that at finite n, these previous papers had a problem. Because at finite n, they were trying to study this theory, but you literally can't do these integrals, because the integrals diverge. And so somehow you have to figure out a way of regularizing the matrix model around these singularities. Finally, yet another technical challenge is that notice that the leading term, in terms of this eigenvalue, has a fractional power. Because remember, this delta bar for the various theories takes these forms. This is basically the Coulomb branch operator dimension. And so this is very unusual. Because in every single example of localization, which leads to matrix models in physics, you always get an eigenvalue to the power 2. Or maybe in some cases to some higher integer. But you never get it to fractions. That's very unusual. In fact, I'm not even sure if in physics in general people have ever discussed matrix models which have fractional powers. So I was looking through the literature, and I found a couple mathematicians who had studied these cases, but it's very obscure. And there's a very small literature about this. And so this is very weird. In some sense, you could say physically, this fractional power is related to the fact that you have this kind of certain number of D7 branes. And so in particular, if you were to generalize this story to the D4 case, then this delta bar is actually 2. So in that case, it would be an integer. And that's related to the fact that localization exists. Whereas for these cases, there is no localization, and so you get these weird fractions. Okay, so we have all these challenges. This is a very hard problem. And so we cowardly only look at one term in the large N expansion of the mass to form free energy, which avoids these problems. So in particular, we're going to look at this leading term, which is going to end up going like log n. And so we're going to compute the log n term, but we're not going to compute any other terms, even the n to the 0 term. So why is the log n term particularly simple? Well, it turns out that if you take this expression and you take derivatives in terms of mass, you just want to look at log n, then you only have to consider the terms written here. Basically this term. Nothing else contributes. And in particular, you only have to compute a 2-point function in the matrix model. And what's nice about 2-point functions is that they take a universal form for any matrix model. This is related to something called a Bergman kernel, which is some kind of deep fact about matrix models. And so even for our very funny fractional power matrix models, you can use these formulas. And after doing a very natural analytic continuation to get the 2-point function of log u, you get this answer. And so you get that the log n term is proportional to delta bar with a factor of 3. And so then you can use this answer for the log n term to fix the coefficient of the log n term in the holographic correlator, and then you can take the flat space limit, and lo and behold, it precisely matches the expectation from flat space, which came from the tree graviton exchange and the one-loop gluon exchange. This is a very non-trivial check on this proposal, because the fact that this delta bar is appearing means that this very intimately depends on the string theory construction. And so on the one hand, you could say that, okay, this is a check that we've been able to compute the logarithmic divergence in ADS. But I would say more interestingly, this is a check that the matrix model we wrote down makes sense. And so even though it has all these problems where it has to be regularized and there's infinite terms and there's a weird fractional power, nonetheless, it's giving the right answer. And so this means there really is something real going on here. Yeah, because remember, delta bar is related to nu, which was like this, which was like, yeah, like it was basically how different from the sphere you are. It's also related to the number of D7 branes. I mean, all these things are related. It's all kind of like the same concept. Okay, so to conclude, what we did is that we fixed the large n finite tau expansion of gluon scattering for various F-theory duals. In all cases, we computed the log n term, and it matched the flat space limit. In the D4 case, where we had a Lagrangian, we were able to compute the f to the 4 correction in terms of Jacobi theta functions, which we also matched the flat space limit. And we were also able to compute all higher corrections at genus 0, i.e. the ADS Veneziano. In the non-Lagrangian cases, we proposed a novel matrix model for the free energy using the Seiberg-Witten curve, and we have a consistency check for the log n term. We also initiated the finite n and finite tau numerical bootstrap, so far only for the rank 1 D4 theory, but in the future we hope to do it for these other theories. So future directions. First of all, for the D4 theory where we have a Lagrangian, it would be nice if we could find a finite n and finite tau generalization of these mass derivatives. So this was done in n equals 4 super Yang-Mills for the 2 mass derivative case by Daniela, Konkow, and Michael. And so considering that this theory seems to be much simpler, so that means hopefully it should be even easier to find the finite n finite tau than it was here. Because after all, right now we know the answer to all orders in 1 over n and finite tau. So all we're missing is exponentially in n terms. So we're kind of very close to getting finite n and finite tau. So that shouldn't be too hard. Although these exponentially in n terms probably depend on tau. So for the non-Lagrangian theories, there's many things we would like to do. I mean, so first of all, we'd like to systematically compute all corrections to the matrix model potential, probably by some kind of holomorphic anomaly equation. And if we could do that, then we could fix the n to the 0 correction to these mass derivatives, and thereby be able to fix the f to the 4 correction to the holographic correlator. And there's even some flat space predictions we'd be able to match to. More ambitiously, if we could compute all 1 over n corrections to the mass form free energy, then this might give a good approximation to finite n, which could then be used to numerically bootstrap the theory just as we did for the D4 case, which is ultimately what would be necessary if you want to study unprotected corrections. Finally, it would be nice to compute the ADS tree graviton exchange term, because that will be necessary to get f to the 4, because it also shows up at order 1 over n squared. This is something I'm working on at the moment. Finally, I just want to emphasize that this method of combining bootstrap and localization is extremely general, because it applies to any 4D theory in which you can do localization, and apparently it even applies to theories where you can't do localization, but where you have the Seiberg-Witten curve. And so we've only studied a very small amount of theories so far, but there's many other theories to study. So for instance, we could study SUN, SQCD with n bigger than 2. We could try to understand its large n limit, etc. All right, so that's it. Well, I mean, it depends on your group. Because if you only have one quarter Casimir, then they're related. So you have as many f to the 4s as you have quarter Casimirs. Because because f to the 4 literally is a trace of 4 generators. So as many quarter Casimirs as you have is the number of f to the 4s you have. So for the SOA case, you have 3 f to the 4s. You could think of it as like f squared squared, f to the 4, or the Pfaffian of 4 f's. For the other theories we consider, you just have 1 f to the 4, because there's just 1 quarter Casimir. Because like f squared squared is just trivially related to f to the 4 in that case. For SUN, I think there's two quartic Casimirs, and so I guess you would have two different kinds of f to the 4s. I'm pretty sure they're both protected. Yeah. So for d squared f to the 4, it's a bit more complicated. So d squared f to the 4 is kind of like the last term, which is still protected, and I guess indeed it's only protected in some cases. But um, yeah, but the thing we mostly talk about is f to the 4.
On a number of your transparencies, I remember 17 and 19, you had an undisclosed function little f sitting after all of your logarithms. You said it was known. What's the point of it? How does it behave?
Okay, this is an excellent question. So this function was computed by Arkady Zeitlin, Gregory Cherchemsky, I think Gerald Dunn. You may have also been involved in that. I know there was two papers. I forget which one was which. Um, and so that function is written in terms of Barnes G functions. But it doesn't depend on tau, which is why, and also it's kind of subleading in n. So like when you expand this function, f of n, it starts at 1 over n. And so it doesn't affect the order for which I care about, although it's certainly an interesting function. Okay, so that's an excellent question. Is that what happens at finite n? Um, I forget exactly what goes on with this function. I don't remember its singularity structure. It might have some divergences at. Yeah, sorry. I should have also cited the other paper with Gerald. Sorry about that. There's two papers. Well, I guess this was the second one. But anyways, so yeah, it's a function of Barnes G functions. I don't exactly remember its singularity structure, but like it's definitely true that if you take this formula and you try to compare it, because like for finite values of n, you can just compute the matrix model numerically. And so you kind of know the answer. And so you could try to compare, say for n equals 2, to this large n expansion, which is to all orders. And the large n expansion is not very good, at least when the coupling is small. When the coupling is strong, it is good because that's what you expect. But when the coupling is small, which is where this expansion you don't expect to be so good, then in fact, it doesn't match so well, which is kind of implying that the large n instantons are big, and they depend on tau. And so that's kind of the thing which is missing right now. And that might be related to resurgence and I guess the various topics of this conference. On the other hand, though, like it might be possible to guess it because like after all, you know that the answer must be modular covariant. It's a strong constraint, and like already we have a Toda equation, which is how Arkady and collaborators were able to derive the large n, large lambda. So like maybe there's like an upgraded tau version of that. Yeah. So okay, so I was a bit quick there. So basically, the point is that 2-point functions in a matrix model are all computable for some kind of universal formula. So it's like if you want to compute, okay, so like imagine you have a matrix model whose eigenvalue is u, then you could compute the 2-point function of u to the k and u to the m for any k and m, and there's some like exact answer for that matrix model 2-point function. And so if you could do it for any u to the k and u to the m, then you could take the limit where like, you take derivatives of k and m, and then that gives you also the 2-point function of log u and log u. And so, but the basic idea is just that like all these 2-point functions take a universal form, and they don't care on the specifics of the potential. I mean, they care on a potential like a very simple sense, and so this is why like the fact that the fraction was like delta bar over 2, it ends up just being kind of an overall factor. That's where kind of this. Basically, what we did is that we rescaled u by n to the delta bar over 2. That put an n out front, and then so basically here we rescale by n so that you'll have an n over here, and then there's also an n over there, and then we take derivatives of masses, and so this brings down 2-point function of log u, and then we compute the 2-point function of log u using this universal formula, which I don't write down, and then that gives this answer. But if we were to want to compute the O1 term, that would involve other higher point functions, not just the 2-point function, and that would not be universal, and that would be more challenging. So having looked through the literature, it seems like people have studied matrix models with fractional potentials using orthogonal polynomials. So there's a class of orthogonal polynomials that actually works in that case at finite n. But the problem though is that at finite n, this matrix model has other problems, which is that we don't exactly know how to define it, because there's like divergences at u goes to 0. Um, and so probably large N is the best defined version of this. Now, the idea of you having matrix models that are defined at large N but might not be defined at finite N is not such a weird thing, because this shows up in physics. So it's like when you study like two-dimensional quantum gravity, it's very common that you'll have matrix models which are only defined at large N. And so that's probably the case here. And so my guess is this matrix model only makes sense in a large N expansion, but it could be the case that it makes sense to all orders in 1/n, and then that might even be a good approximation for finite N. Um, which would be very nice, because then you could do numerical bootstrap at finite N using this. Sure. Okay, so these are all good questions, and so I don't really know the answer. I mean, so like the eigenvalue distribution would probably relate to how you try to regularize what goes on when u goes to 0. Yeah, and so like, I mean, this is something. Well, yeah, I don't know the answer. I mean, this would be a good thing to look into. Uh, I mean, like, you could make some kind of simple conjecture. You could say, okay, maybe it's like a one-cut matrix model or something, and then I guess you would have whatever follows from having this weird power. So you'd have some kind of like modified, I guess, like Wigner semicircle. Um, but it ends up being more complicated. It's no longer just like a square root. So it's like, so this was done in the literature. So it's like, if you just want to compute kind of like the leading saddle point expression for the eigenvalue density, it involves a hypergeometric function. So we have a few comments in the paper about that. And then that hypergeometric function just simplifies specifically in the case where this power would be 2 to then being the usual Wigner semicircle. But other than that, it's a hypergeometric function. So there's some partial results in the literature, but then again, that also kind of is assuming whether or not it's a one-cut or two-cut matrix model. It might be that this is some like multi-cut matrix model, because of these divergences. Yeah. Okay, so one reason might be that open string theory is simpler than closed string theory. And so we know this from the amplitude perspective, right? The Veneziano amplitude is much simpler than the Virasoro-Spira amplitude. And so what we are studying here, so I'm not going to claim that the full theory is simpler than the full n equals 4 Sabourin Mills, but we are focusing on like a sector of the theory. So we are focusing on the 4-point function of the flavor multiplet, which is dual to gluon scattering. And then the intuition from the bulk is that gluon scattering should be simpler than graviton scattering. And so like the way in which it is simpler all had to do with this specific 4-point function. So for instance, we claim that the mass to form free energy is simpler, where these masses are the things that couple to the flavor multiplet. Now, if we would have done deformations that couple to the stress tensor multiplet, like turning on squashing, then the theory would be even more complicated than n equals 4. So it's only because we're turning on masses coupling to the flavor multiplet that it's simpler. Now, a technical reason why that is true is because these gluons, well, basically these masses correspond to fundamental hypermultiplets. And so fundamentals, the way they enter the matrix model is just much simpler than, say, adjoints, as in the n equals 4 case. So in particular, fundamentals deform your matrix model by a single trace term in the potential, whereas adjoints deform it by a double trace term in the potential. And so this is why our case is simpler than n equals 4 Sabourin-Mills. So that's kind of a technical explanation, as well as like a possibly physical explanation. But I think the intuition is just open string theory versus closed string theory, because this theory is, as far as I know, like the only ADS CFT example which allows you to study open string theory without introducing like defects and non-local stuff. I mean, it's this theory, and there's a couple slight variations of it. You can also take various like discrete orbifolds, but like basically this theory is the theory if you want to study open string theory using ADS CFT.